Hey guys, welcome to video 89. This was originally video 80, but I meant to edit that video to correct something, and I discovered that you can't edit a video you've already posted. It just gets deleted and you have to repost it. So what's happening here is I'm just going to repost video 80 now as topic 89, and it doesn't really screw up our continuity too badly. We were looking at push-pull amplifiers anyway. This just doesn't have parallel tubes in the output stage. So running through the circuit real quickly here, all of the values in blue boxes were the theoretical values that we designed for back in video 79. The red boxes are the values I got from the experimental circuit. Starting at the output here, we can see that our plate current is in pretty good agreement. We got a little bit less than predicted, but it's really not too bad. Our cathode voltage is a little bit lower than predicted. Again, we have slightly different parameters for our tubes than we used in our design value, so that's not unexpected. Now, as far as the screen grid current goes, it's about 50% lower than we predicted, but we were using just an estimate of 25% of our design goal plate current, and in reality it's a bit lower, but it really doesn't hurt anything. It's just fine. And notice that we didn't use bypass caps on our screen grids, but for a guitar amplifier that usually doesn't present any problems. Moving over to the left, we've got our phase splitter, and this circuit was designed back in video 67, so if you want to see the details of the design, you can go back there and look. The equations that are pertinent to the phase splitter are shown here. Remember, we had two versions. We could take the output on the cathode side directly from the cathode, in which case these equations are applicable, or we could take the output from the junction of RK1 and RK2, in which case these equations are applicable. In our example, we used version 1. And let me come back to our schematic. You can see here. And this circuit has a gain of approximately 1 on each output terminal, plus or minus 1. So we're just going to estimate the gain of the phase splitter as being 1. Coming back over to the push-pull section for a minute, the AC design and analysis equations we'd use over here are given on this sheet. And we can see that the overall voltage gain of the push-pull stage is 2 times A prime V, that's the gain from plate to grid for each tube, times the reciprocal of the total turns ratio. And as we can see over here on the right-hand side of the schematic, NP is equal to 2 times N1. It's twice the number of turns for each half of the primary. Now let's go back to our original schematic, and if we take a look at the boxed values over here, the theoretical voltage gain should be 3.3. The measured value is 1.6. That's normally the one that will be in biggest disagreement, but we're not looking for a lot of voltage gain out of a stage like this to begin with, so anything we get here is good. Our maximum output voltage theoretically was plus or minus 10 volts. We got plus or minus 8.9, and that's not bad considering the idealized version of the transformer and the tubes that we were using in our analysis. Maximum theoretical output power 6.25 watts RMS. Actual 5 watts RMS. Again, that's not too bad. Now, actually prototyping a circuit like this for an experiment is kind of difficult sometimes, so let me show you what I did to make life a little bit easier for myself. I took an aluminum chassis and I mounted 3 9-pin tube sockets. These two on the top here are for the EL84s. This middle one is for the phase splitter. And these two 8-pin sockets are wired in parallel with these other two so that I can also prototype circuits using, say, 6V6s or 6L6s. All right, over here I've got a power transformer that's going to give me a 250 volt supply rail, and this is the bottom view of the box. I mounted some terminal strips in here for wiring purposes. Here's the filter cap for the power supply, my power switch, and a power indicator. And if we slide over a little bit here, you can see the finished product. Most of the resistors you see here are part of the phase splitter circuit. This 100K 2-watt resistor is just a bleeder resistor for the power supply. And over here I installed a rotary switch so that I could put different dropping resistors in series with the supply to get different voltages for other experiments. Now if we come over here to the next photo, here's the actual breadboarded amplifier circuit, and coming out the front here I've got the screen grid and cathode power supply and ground leads, and they're running over to the proto board. And over here I connect my output transformer, and this is my 8 ohm load resistor that I'm using to test the amplifier. And also I installed a little RCA jack here that feeds into the phase splitter. That goes over, and my function generator would be connected to it over here. Okay, let's go look at some waveforms from this circuit. And we'll start out here with 1 volt peak to peak coming in at 1 kilohertz, and we get a V out of about 1.6 volts peak to peak. So our gain is 1.6, and our max V out is 0.78 volts, minimum negative 0.79. So we've got pretty good symmetry here, very little distortion. And now let's see what happens if we turn the input voltage up to 10 volts peak to peak. Here we can see we're getting about 7 volts out on our maximum and -7 on our minimum. So again, it's a pretty clean, undistorted output voltage. The gain is a little bit lower now. It's about 1.4, but everything's looking good. So now let's turn it up a bit and see if we can get some distortion here. With 15 volts peak to peak applied, we're now starting to see some clipping occurring. It's pretty soft, but we are getting pretty much symmetrical clipping on the top and bottom. We've got about a gain of 1.1. So as we drive the amplifier into clipping, the voltage gain will drop. We've got 17.7 volts peak to peak out. And if we take it a little bit further and really overdrive it with 20 volts peak to peak, we can see we're getting pretty decent hard clipping, and our maximum output is 18 volts peak to peak. VO max is 8.9, VO min negative 9.3, so we do have a bit more asymmetry and nonlinear distortion going on. Now let's go on over and look at our response with 10 volts peak to peak applied. And something you might be wondering is what would happen if we took the cathode bypass capacitor off of the circuit. And that's what we're going to look at next. I did remove the capacitor, and this is the resulting output I got with 10 volts peak to peak coming in. And you can see we still get a pretty good output. It's not much different. We had about 14 volts peak to peak coming out with the bypass. We've dropped to about 13.6 volts peak to peak, so it really hasn't made much difference. And in order to make it easier to make a comparison, I put both traces side by side. The yellow traces are the ones we're interested in. The blue is just the input. It's on a different scale. I should have changed it to make it the same. But in any case, with cathode bypassing, we're getting about 14 volts peak to peak out. With no cathode bypass, we're getting about 13.6, and the waveforms are basically the same. Now let's take it up a little bit to 15 volts peak to peak, and when we remove the bypass, this is the comparison we've got. Our gain is about the same in both cases. There's very little difference in the output voltage waveform. So apparently the bypass cap on the cathode really doesn't make that much difference. If we had more asymmetry or mismatch between the two output tubes, it might matter more. But if they're reasonably well matched, it really doesn't seem to make that much difference whether we bypass the cathode or not. Now, I set the scope to function as a spectrum analyzer here, and I just did it on the version with full cathode bypassing with 10 volts peak to peak, and this is the display that I got. So again, with 10 volts peak to peak coming in, 1 kilohertz, we get 7.1 volts RMS for our fundamental on the output. The second harmonic drops all the way down to 0.03 volts RMS, and our third harmonic is up a little higher at 0.18 volts RMS. And we can see we do have, the usual assortment of even and odd harmonics up here at higher frequencies, but they're very small. So overall, our total harmonic distortion with 10 volts peak to peak coming in is about 2.6%. Now, if we turn the amplitude of the input up to 15 volts peak to peak, our overall total harmonic distortion increases to about 8%. And again, we can see how the voltages are distributed among the different frequencies here. Now, if we increase V in further and further, we're going to drive the amplifier into harder and harder clipping. And what that's going to do in the spectrum is cause the odd harmonics to be accentuated more because of the symmetry of the output waveform. And that's a topic we'll talk about in another upcoming video. But for right now, something you might be curious about is what happens if we bypass the screen grids, and here's what we get. If we apply an input voltage 5 volts peak to peak and we bypass both the cathode and the screen grids, here's what we get out. So our voltage gain is up a little bit. It's now 2.2, and the output is very symmetrical and clean. So it looks like we just get a little bit more gain, and as far as linearity goes, it seems to be pretty good as well. Now, if we increase our input to 10 volts peak to peak, we can see that our gain does drop a little bit, but we're getting about 18.5 volts peak to peak out, so we are getting a little bit more voltage out with the screen grids bypassed. And finally, if we take it all the way up to 15 volts peak to peak, we can see we're getting relatively hard clipping. We've got 19.5 volts peak to peak out. That's more than we got previously. So bypassing the screen grids increases the performance of the amplifier a little bit. It gives us a little bit more output voltage swing, a little higher voltage gain, and this is really very, very nice symmetrical clipping as well. And just for your convenience, I redrew the schematic with these modifications made, and here it is with screen bypassing and of course bypassing of the cathodes. And because our output voltage jumped up a little bit, we're getting actually very close to 6 watts RMS out of the amplifier at full output. Now, one other change I made here that you might have noticed is that I bumped the screen grid resistors up from 10K to 20K ohms. I did that just kind of as an experiment to see what would happen, and it really didn't make any difference in the performance of the amplifier. So you can go with 10K or 20K here, it really doesn't matter, but I left 20K in the schematic. Now, all the currents and voltages I have listed here are measured values I got from prototyping this. So if you wanted to build it, these are the values that you would probably come up pretty close to. And finally, let me leave you guys with a homework assignment. It's basically the same amplifier. I bumped the power supply up to 300 volts, and we're shooting for 35 milliamps plate current for each EL84. The input section is going to have to be redesigned a little bit because we've increased the power supply voltage. We're shooting for 225 volts at the plate of the 12AX7, 75 volts at the cathode. And lastly, determine what output transformer you're going to need for this circuit, and you can look at Hammond or Edcore or whoever and find the appropriate transformer you need. And that's it for today. I will see you guys next time around.